The central Himalayan seismic gap has remained locked for centuries, with no major rupture recorded since the massive earthquakes of 1344 and 1505 CE. For 700 years, the Indian plate has continued its slow collision with Eurasia, steadily accumulating tectonic strain in this specific region. This accumulated energy sits directly above the densely packed urban populations that occupy the valleys and plains of the Indo-Gangetic region. Recent integrated geodetic studies now indicate that the energy stored within this gap is physically capable of producing 2 magnitude 8.8 earthquakes. Quantifying a threat of this scale requires moving beyond historical estimates and utilizing advanced orbital radar and deep Earth seismic models. Historically, tectonic strain in the Himalayas was measured almost exclusively through horizontal surface velocities using GNSS. This data tracks the lateral shortening of the crust as the Indian plate pushes into Eurasia at nearly 40 millimeters per year. However, horizontal movement cannot accurately resolve the depth or total width of the locked portion of the fault buried deep underground. Measuring the missing variable, vertical land deformation, across the steep and chaotic Himalayan topography was notoriously difficult for ground-based sensors. Without precise vertical data, structural engineers and disaster planners remained blind to the true volume of rock actively storing elastic strain. To solve the vertical measurement problem, researchers turned to ALOS-2. This satellite utilizes interferometric synthetic aperture radar, or INSAR, to capture millimeter-level changes from orbit. INSAR measures ground deformation by comparing the phase of radar waves between repeated satellite passes over the exact same terrain. Analyzing 87 INSAR images revealed a steady vertical uplift signal of 5 to 8 millimeters per year across the higher Himalayas. Scientists cross-referenced this with GRACE satellite data to apply hydrological corrections, ensuring the uplift signal was purely tectonic rather than a result of seasonal water weight. This vertical motion indicates the crust is actively flexing upward, stretching over a locked fault below. This elastic loading perfectly aligns with horizontal shortening data. Integrating this 3D velocity field extends the locked zone to a staggering 115 kilometers. North of this 115-kilometer stretch, the fault transitions into a creeping zone where friction decreases and the plate slides steadily rather than storing strain. Discovering this wider locked width rewrites the strain budget, proving there is a much larger physical reservoir for potential earthquake energy than previous models allowed. While orbital radar mapped the crust, advanced S-wave receiver function techniques began uncovering a parallel discovery happening deep beneath the surface. Classical geology often assumes the Indian plate underplates Eurasia as a uniform, solid slab of rock. New 3D seismic imaging proves the Indian plate is actively warping and tearing, particularly in the eastern section. This process, called lithospheric delamination, occurs when the dense lower part of the tectonic plate peels away and sinks into the mantle. As the layer sinks, a molten asthenospheric wedge forcefully rushes in to fill the newly formed void between the separated layers. This molten wedge introduces extreme, localized stress into the crust above, driving the formation of active rift zones like Yadongulu. Internal fracturing within the Indian plate alters the transfer of tectonic stress to the surface, creating highly complex and localized rupture patterns. Combining the vertical geodetic data with these deep Earth stress models allows for a final calculation of the tectonic strain budget. The primary variables for this equation are the 115-kilometer locked zone and the 700 years of elapsed time since the last major rupture. Researchers also utilized a revised slip convergence rate of 20 to 22 millimeters per year, a value significantly higher than older models suggested. Seismic moment accumulation scales directly by multiplying this slip rate across the 115-kilometer locked geometry over the last 7 centuries. This massive potency rate equates to at least 2 magnitude 8.8 earthquakes. If the entire 115-kilometer locked width were to rupture in a single sequence, a magnitude exceeding 9.0 is physically possible. These geodetic findings align with paleoseismic records in the region, which show a history of long intervals followed by exceptionally high slip events. The devastation of the 2015 Nepal earthquake demonstrated the destructive power of even a partial release of this energy. This magnitude 8.8 calculation provides the physical maximum that statutory disaster frameworks must now prepare to absorb. The geological threat extends south of the high peaks, down into the Indo-Gangetic Plain. Major urban centers like Delhi and Lucknow are built on deep, soft sedimentary basins. These soft sediments act as an amplifier, trapping distant tectonic ruptures and increasing their amplitude into long-duration, highly destructive shaking. Massive human density exists directly atop these vulnerable, amplifying layers. Due to this combination of high strain and sediment amplification, India's revised 2025 seismic hazard map has designated much of this region as Zone 6, the highest possible hazard level. This physical capacity for a magnitude 8.8 event creates a strict legal mandate for governmental action. The National Disaster Management Authority holds a statutory mandate under the Disaster Management Act of 2005 to manage this risk. The National Policy on Disaster Management legally requires a shift towards proactive, simulation-based mitigation, prioritizing preparedness over reactive relief. Hard geodetic data, the 115-kilometer locked zone and the magnitude 8.8 limit, directly informs these statutory drills by setting the maximum stress test parameters. This data guided Exercise Suraksha Chakra, an integrated mock drill simulating a catastrophic earthquake across 55 locations in the Delhi NCR region. These drills test incident response systems through real-time evacuations, medical simulations, and NDRF structural deployments. These simulations are designed to test institutional readiness against the physical limits defined by modern INSAR and seismic models. As science uncovers the extreme limits of the Himalayan strain budget, public policy and institutional engineering must scale their resilience to survive it.